National Wellness Seminar. It's a great pleasure to introduce Dr. Ian Levitt. He's a NASA scientist working at NASA Langley, and he's going to talk about from research to reality, challenges and opportunities in complex system design.
Thank you. Thank you, Gilad, and the university for holding these nice seminars. I've watched a couple, and they're really interesting. I hope that this one is interesting as well. I noticed that I chose the same title as the person that came just before me. It must be popular, and it is because kind of I got a couple of maybe things I'm after with the presentation, but in general, one of the challenges in industrial problems is bridging this gap from the research problem to actually making it work in the real world. In fact, it's where most of our failures occur. So I think that it's important to focus on that transition, not only for the researchers and the scientific practitioners, but for the managers and the organizations that are tied to that reality, right, where they need their research to work in the real world. So, I reckon most of the folks here are interested or at least curious about, how do I take my education and skills that I'm building here at the university into an industrial setting. And when you do that, this is the bridge that you're going to be really kind of responsible for tracking. Otherwise, your research doesn't amount to what you want it to. There's also a lot of value in just the research side, right? So it's just a different phase of the mission. So introduction. I'm Ian Levitt. As Gilad mentioned, I'm a scientist with NASA, specifically an airspace researcher. NASA works on multiple domains. One of them is the air transportation system. Prior to NASA, I was working for the FAA, Federal Aviation Administration, which is the regulatory body that is responsible for setting the rules and owning the airspace and keeping everybody safe while they fly. So NASA does the research, FAA does the implementation. And that research to reality transition is significant challenge and something that I've been working on, pretty much for my whole career. A lot of this, most of this presentation is not going to go too deep into details. I would love to get into details. And one of my goals is really to try to establish some interest and some connections because, having worked for FAA and having worked for NASA, one of the things I really like about NASA is the opportunities to collaborate. We have lots of different ways to do it: internships, collaborative contracts. We get very creative with how we can work with other people because that's really our strong suit, right? It's kind of bringing together researchers. So please feel free to interrupt if you want to, poke at something. And I would love to have more conversations afterwards. If there's anything here that you want to go deeper on, just let me know. So we have a little bit of eye candy here. The picture on the top right, the simplified NAS, this is kind of a running joke. That's legit. This is really a diagram of NAS stands for National Airspace System. This is really a diagram that presents one view of the automation systems that run the airspace. And it's simplified, right? Like the real diagram would not fit in the room, right? It's very complex, very complicated. And it's one of the reasons why, you may hear stories about antiquated technologies, right? at the FAA, or now we're hearing about it at the Treasury Department, is because it's very difficult to change these things, right? Like once they work, there's so many interrelationships that to make any kind of improvement, it's a significant effort, and that effort involves doing the research, trying to predict what the needs are for the future, and then translating that into actual reality. And really, everywhere you look is a complex system, right? I mean, I've been 20 years in the federal government, and the government itself is a complex system, extremely complex, right? There are 2 million federal workers. There are, 3 branches of government, multiple different bureaucracies that all interdepend on each other and depend on global dynamics. One change over here has a big impact over there. Here's something that we're working on at NASA, the Moon to Mars. And we recognize, so Moon to Mars is the mission that NASA is undertaking to, basically get us to Mars. And we do that by first establishing a base at the moon, and then using that to get to Mars. And that's NASA, trying to stay out ahead of the curve, right? Like we don't need to go to space anymore. We've privatized that. Now, what's the next step? It's getting to Mars. And we recognized early on that in order to execute something like Moon to Mars, we need an architecture for it. And like architecture for a space shuttle, that makes a little bit more sense. Like I can point to the wing, I can point to the fuselage and different parts of it. But what is the architecture of an effort, right? What is the architecture of a 50-year program or project? So this is just one picture of it, right? And again, just to kind of like show you how, like where the complexity lies. This is the communication and positioning system. Again, just at a very high level. In order to do all the work and maintain all the interconnectedness, there's an architectural structure that we have to leverage. And if we do it right, we can more quickly and efficiently get our research out into reality. So for me, and this is kind of my personal motivation maybe, or like my opinion, like this does not represent my employer necessarily, is one of the key ingredients, I think, to managing the complexity of the future that we're all dealing with, right, or going to be dealing with, because we only have more and more complex interrelated problems that we have to solve. Is systems thinking? I would go so far as to say I would love to see curriculum in schools that start to train our people about how to think about a system, how to think about system of systems and interrelationships, and how systems get built from an early age, because sort of a natural mindset that you might need to have. So I don't know if anybody's like familiar with engineering or system engineering, but this is the system engineering V, where basically on the left side of the V is where you're doing your research, more or less, right? So you're figuring out what your concept is, you're breaking it up into the big pieces, and then you're getting deeper and deeper and more granular in the definition of how's this system going to get constructed, all the way down to the point where you have a design for like your software, right? This can apply in many contexts. This is right now written to be applicable to software design. Once you get all the way down to the bottom, then you build it back up, right? So you implement the code and then you test it and you say, does it doing like the little thing it was supposed to do? You put multiple things together, you test that, is it integrated, is it doing what it needs to do? And it's a V because every time you sort of go up on the right side, you're checking your assumptions across, right? So when I'm doing integration testing, I'm trying to see, when I integrate, did I build the thing that's really doing what I thought it was going to do? And did I think the right thing? This diagram is kind of like a shock and awe case for why we need to sort of think differently, especially when we're in the research phase. The black numbers represent where along this process you introduce something that's suboptimal, right? Like you make an assumption that's wrong, or you introduce some sort of fault. The yellow represents where we actually discover that there's a fault in the design of the system. Traditionally, we introduce almost all of our errors at the beginning, but we don't find them until we turn the corner and we start building, right? And every time you go further and further down the build chain, the cost goes from, to fix the problem on the research side costs 1x. To fix it on the development side costs so much that eventually it becomes prohibitive to even change. And you just have to live with the problem and, get half the benefits that you really thought you were gonna get. So there's this like shifting left that needs to happen from the reality of building it. Like, why do we find all these errors when we build it? Because we've now built something and put it into the world. And there's only one thing that covers every single possible assumption, and that's the reality itself, right? Anything that you do, on paper or in a simulation, there's always some assumption that you're making, and you're not, you really can't test that assumption until you get out into the real world. So, you got the real world on the right-hand side, and in order to solve this problem, you have to push left and connect your research thinking to your reality thinking. So the rest of my talk is just going to kind of like hit on a couple of problems that I think maybe give an example of where mathematics. There's one more thing I wanted to say on this slide. So I want to give some examples of like, a little bit more specifics of, some problems where mathematicians can help out, or some problems that I've encountered that have been, maybe just fun to work on mathematically. But my punchline for this slide is that I've said from the beginning of my career that everybody needs a mathematician in their group. Like, I don't know if this is all math department or like, you got folks from other departments or not, but you got to have a mathematician on your squad. Just because the mathematicians have that abstract thinking that like kind of provides that connectivity on this research side. This is my case for everybody should hire a mathematician, because they're curious and they'll help root out those problems. So this is probably like my first fun math problem that I worked on when I went to the FAA. There's a system called air traffic control radar beacon system. This is how we know where aircraft are. There's the radar systems go around and they actually interrogate this system that's on the aircraft, and the aircraft broadcasts a radio frequency signal. It's an old system, and it's just by what's called pulse modulation. So it's just sending out pulses that are of a certain structure, and that structure tells you like information content in the message. And the main thing that tells you whether you've received one of these things is the timing between the first pulse and the second pulse. So here's like a picture of what an ACRABS message might look like. You got a first pulse, you got the last pulse, and then all the stuff in between is like the information content. There are multiple airplanes all in the airspace. They're all broadcasting, and all of these ACRABS are arriving at your antenna, and they're all stomping on each other. And you're going to be trying to do your best to decode as many of these messages as you can, so you can track all these aircraft accurately and with high reliability and safety. So one of the things that happens or can happen is you get another message that comes in. So here's a red message, right? Again, framed by the two framing pulses, and you find those two red pulses, and you're like, okay, there's a message, and I found the blue message. But I might also find another message that wasn't really there, right? False detection of these two, but they just happen to line up in a certain way. So the problem that I walked into, it was like, one of my first problems on the job. We had engineers who were measuring the environment, and they needed to know how many messages are hitting my antenna per second, right? Because that's going to tell them how many aircraft are out there, and it is going to answer all these engineering problems that they needed to know, right? So they needed to know how many messages are in this data set. But they knew this false detection rate was like a problem, but they didn't know how to figure it out. So they're trying like all these ways to like estimate or like calibrate and get it as good as they possibly could. But it turns out there's really a simple mathematical solution, because the nature of these arrivals is that they follow a Poisson process, right? Just like the buses do. And so once you recognize that, you see it's actually kind of an easy combinatorial probability problem to figure out what's the probability that you're gonna, that two messages line up to give you a false detection. And in 2 days, we were able to come up with a little calibration tool that lets you say, if I measure 15,000, the answer is 10,000 because of this. It was a little more complicated than that, but it was simple and it was exact and it was very satisfying. And anyway, just thought we'd start off with my, the fun problem. All throughout these slides, there's a bunch of links that if you're interested to go deeper on anything, you can follow them. And of course, always follow up with me. So now a little bit closer to what I'm working on now at NASA. So again, we recognize that the architecture of the aviation system is important. I can talk about the architecture of an airplane, that's easy. I can kind of talk about the architecture of like a building that has, people in it that are controlling traffic, that's kind of easy. But there's more to the system than that. And it's massive and it's complex. And it's changing. So we're on the cusp of transformation in transportation that's being pushed by advances in technology that we're seeing everywhere, AI, machine learning, data everywhere, gives us the opportunity to do a lot of things that we hadn't been able to do before. Electrification of aircraft, we're now able to, because they're not certified yet, but we're close to having aircraft certified that allow you to like actually fly in and out of urban cores without tons of pollution and tons of noise, which opens up a whole new opportunity space for aviation. But some questions that are as simple as, should this operation happen? Like, is there a benefit to the user or to the society for this operation to happen? You have to analyze that in a bigger picture. So like even looking at the aviation system is not enough. You have to look at bigger and bigger systems like the transportation system to know, should I fly or should I take a bus? Like which things should we be investing in? And if we're going to change something, how are we going to change it without disrupting the safety that we have already? And in these environments, right, the FAA, who's responsible for building these systems, is a complex organization full of people of every type and size, right? I mean, you've got scientists, you've got engineers, you got, business people, you've got the whole spectrum of skill sets that all have to also work together, to change a thing. And so one of the big challenges is simply language. Like, are we all using this word in the same way? So what we're doing, one of the things that we're doing at NASA is trying to develop sort of an evolved, an advanced version of the aviation system architecture structure that addresses some of those problems. One of those problems, for example, is simply being, are we all using the same term, right? Like when we talk about capability, are we all thinking the same thing? Because we're just thinking like close to the same thing, we might end up in different places and not realize it. So one of the approaches, one of the ingredients to doing this is bringing in what's called the basic formal ontology. Folks may be familiar with that. I don't know. It's a top-level ontology that was developed and continues to be developed out of University of Buffalo. Recently adopted as like a requirement by DoD. If you want to get a DoD project, you have to cast it in terms of BFO. So we're starting to apply that to aviation. we're identifying like what are like the really important terms and what are the really important things for us to model. And that leads to, this is, again, it's eye candy, but this is real data. This is the data that, some of the data that we put together that represents that complex system and allows us to sort of manipulate the data, understand at a deeper level what's going on within the architecture, and gives us some formalism that we can base better tools or better engineering processes on. For example, the move to model-based system engineering or digital engineering. Again, this is something I don't know if folks are familiar with it or not, but if it strikes interest, I'd be happy to talk about it more. Traditional engineering techniques involve a lot of spreadsheets and paperwork and tracing requirements and making sure every step is perfect, and it's a lot of information, a lot of data. And we found that operating with models instead, right, diagrams and pictures are much more effective. So here's just an example out of literally something we were doing last week. I just thought I'd throw it up there as an example of how we use this terminology and use the objects that we've defined in the data set to reason about the architecture. In this case, we were asking the question, there's something called the separation provision intervention capability. So capability is a very specific thing. Separation provision intervention is the capability that the system has to intervene when there's a potential conflict and solve it. And the question we had was, first of all, what are the pieces that make that up? And then second of all, how long is it going to take to resolve that conflict? And when you have the data modeled this way and you're able to visualize it through these types of models, it becomes pretty straightforward to answer those questions. And I'll talk a little bit more about some ideas and hopes that we have where the machine can start to do these reasonings rather than the engineer. So here's an early example of where we kind of did that a little bit. So this is from 2022, when large language models had just come out. And we had this data set for the architecture that we had built. And we wondered, can we use it to speed up the engineering process or do things with the engineering process that are onerous or maybe that we just don't do today? And we thought the large language models might be useful for that. So, everything starts with the concept of operations. Everything starts with, human reasoning, human language, human description. And that's where large language models tend to live right now, right? Like your ChatGPT applications, they're generally digesting tons of textual information and then trying to pretend like it's a human. But we're architecting and we're engineering, right? And our whole first step is to take this human stuff and turn it into machine stuff, right? Or turn it into formal stuff, formalize it. So this picture right here is just one of the schema that's part of our architecture. And using that schema, we have a database of information. It's sort of coded it as a knowledge graph, and brought in ChatGPT, trained it on some of the data that we had, some of the data that we didn't have. Right, it took a lot to experiment with because it wasn't really built for. It didn't seem to be built for this type of structured data. And we used like kind of a simple approach, which I think characterizes a number of approaches in this area. Where what's the problem? The complexity problem is the database, right? Like it's so complex, and if you want to get some information out of the database, you generally have to bring in an expert who can write the query. So we wanted to have more of a human interface where the user can ask regular questions, and then the ChatGPT turns it into a database query. And we had some great success. And it turned out we actually were able to use it to discover missing requirements, and to flag requirements that might be right or that might need some investigation. And then we bring those back to the system engineers, and we would tackle it in sort of the traditional way. So the machine wasn't doing everything. But this was a lesson for us and for me, that in the power of the formal structure that we can put in, right? Typically, you got to train large language models on massive amounts of data. We got this to work with like 350 requirements. It wasn't a lot of data, but it was a lot of structure. There were a lot of using the schema. And again, this was back in 2022. There's been a lot of advances since then. And that's what kind of leads us to the smile on the face. The latest piece that my group is getting into is applied category theory. I am really excited about this field. My favorite part about it is that it's an opportunity for me to learn something, which I didn't think I would get to do as I got older and older and older. But my training was in combinatorics, and category theory was the one that just was just like, I just zoned out. Did not like it, did not understand it, didn't stick with it. But again, there have been a lot of advances in category theory since, over the last 20 years, and in particular, applied category theory, identifying applications to real world problems. And the reason why it works so well in our real world problems, especially as we look at more and more complex systems, is because of the things that have, the nature of category theory allows you to think and talk and do in important ways. So abstraction is really important, right? There's no way I can talk about the whole NAS at a time if I haven't abstracted away details. But what are the right details to abstract? That's the challenge. You abstract, because it's got to still be meaningful. So moving between like logical architectures, conceptual architectures, physical architectures, category theory provides tools that let us do that. Compositionality, it's critical to be able to take subsystems and compose them. In fact, if we want to figure out how to change the system, oftentimes we're looking for novel ways to combine subsystems. Not to go too off tangent, but there are examples in other domains where we do have artificial intelligence, sort of looking for novel ways to compose things, like in protein discovery, for example. So we think the same type of thing could happen for transportation architecture. While we sleep, the system could experiment with different forms of the system and maybe find that really great idea that we could move towards implementation. And also formalism, right? So category theory, ontology, they kind of work together for me, for us. And the formalism that it brings in lends rigor to what is fundamentally an error-prone problem because of how many humans are involved with it, how much subjectivity ends up coming into the problem. So when we are able to get more formalism involved, we're able to ensure correctness, and we're able to. We haven't experimented with this yet, but this is where I would like for us to go. Start to apply AI and ML to that new structure that we put together. Another thing that's not on this slide that, again, whether it's transportation or just any enterprise level effort, systems tend to work better when you have repeated patterns at all levels. And that's another thing that category theory is very good at. It's good at sort of finding and dealing with and connecting patterns across things that may not seem so connected. Like it sort of blew my mind earlier in my career when I realized that, if a project is building a thing, the project needs to be organized the way the thing is organized. So if you're building a car, the car's got an engine, you need an engine department. The car's got doors, you got to have a door department. Those types of patterns, right, where the pattern of the structure of the car and the pattern of the structure of the people building the car are connected, are really important, actually, if you want to get this stuff done. So there's a lot of promising applications. So the diagram on the left, I should maybe say just something about it. Like the point is, like, this diagram commutes. This is an example of, some of the modeling reasoning that we use, where the squares on the top are what we call the performers. The ovals on the bottom are what we call the behaviors, and performers make the behaviors happen, right? And when you build your system, you come down, you make all these design choices, and you decide which performer is going to be responsible for which behavior. And you want to understand the system at like the highest level, and then decompose it down. And you might want to decompose the performers, or you might want to decompose the behaviors. The top left image is the highest level description of another capability called demand capacity balancing, where demand capacity balancing is the ability to resolve imbalances between how much demand there is and how much capacity you have to service the demand. Really important problem, because the naive ways of doing that, like we'll just wait until the queue clears, is super inefficient. You have to find much more sophisticated ways to manage the demand and the capacity. But you see how simple, like the original, like the top level conception of demand capacity balancing is. You're just identifying demand, you're identifying capacity, you're seeing if there's imbalance, and then if there is, you execute a solution. That's what TMI means, and it's this sort of loop. It doesn't take too many layers down to get to the point where you're like, okay, now we're solving a problem. So anyway, whether I decompose the performers and then the behaviors, or the behaviors and then the performers, I should get to the same thing, and I do. Some of the applications are, being able to take the encoded data and produce different views of the information, whether it's, a system view, a wiring diagram view, or I won't get into all that boringness. Transforming between models, you might want to be able to, look at architecture A, architecture B, do trade-offs between them, or maybe you want architecture A to transform into architecture B over time. So, what are the incremental changes to go from A to B? Category theory gives us a way to talk about that. It gives us a way to connect the abstract concept to the concrete implementations in meaningful ways. It helps us capture system dynamics, system evolution, and some of the really fun problems that we're trying to solve is, you could apply one type of you could apply one category definition to generate wiring diagrams, maybe another category definition to handle functorial data migration, but they're all on the same fundamental things, right? The behaviors and the performers and the fundamental pieces of the architecture. The relationship between those different categories is there's a lot of rich problems there. Okay, so I'll go to the last one. Well, maybe I think I said my punchline, but and it's kind of on the slide, but again, I think there's a lot of opportunity here, where I would and for the NASA level vision, right, which is to say, like, how are we doing things 50 years from now? It's around having this type of structure begin to reason for us, right, and bring in artificial intelligence, machine learning, whatever the technologies of the future are, and you know, approximate simulations. Like instead of going off and building a simulation and, you know, spending all that money and taking all that time, maybe based on simulations that have already been done and are encoded and are, you know, part of what the machine can read, the machine can now start automatically reasoning. So again, I don't know why, I just wanted to pitch that, you know, put a emphasis on that, because ultimately that's where I think this gets us. I think it gets us to the Iron Man, you know, system of the future, where you're, you know, you're able to really experiment internally with the computer, and come up with come up with solutions rapidly. For example, I know I keep saying I'm going to get off this slide, but for example, think about what happened during COVID, right? Everything got shut down. Nobody anticipated it. We learned a lot of lessons from it. The supply chain got, you know, just broke, right? If we had a model of the distribution system better encoded, and we had tools available to us to rapidly experiment and figure out how do we adjust the supply chain, it might not have broken that bad, right? We might have been able to implement solutions faster. And that really is kind of like one of the fundamental problems, like speed with engineering, is you solve a problem today on paper, you don't implement it for 10 years, and the world has changed. All right, last one, and then I'll shut up. This is, again, you know, another sort of piece of the architecture work that we're doing. So NASA's really focused on the research side. And every time we do some research, every time we, you know, execute a simulation that generates data that tells us something about the world, that should increase our knowledge level, right? Like we want to feed that back into the machine, and now we're smarter. And we generate this data in all different kinds of ways, right? Like we can just do a fast time simulation that models everything under one roof and use Monte Carlo it, and it comes up with some low fidelity but telling answers. That would be an example of like a TRL1 or a TRL2 system. So TRL, technical readiness level, it's fairly, it's a very common scale that was developed at NASA to characterize the level of maturity of a system that you've developed. TRL9 means you've crossed the barrier and you're now operational. You're in reality. But before you get to TRL9, you might be doing low-level simulations, or you might develop an actual prototype that, under the hood, you know, kind of waves its hands at a couple things. Like there's not really communications in there, but there is, you know, the real software that would be performing certain computations. So these are like, you know, different places you might find yourself on the TRL scale. You might be designing a prototype that's meant for flight, but you never test it on a flying aircraft. And then once you do test it on a flying aircraft, you've increased the technical readiness because you've proven it does the thing it's supposed to do, even when you're at 30,000 feet. TRL scale has been really, you know, foundational for the engineering community. It remains subjective, and sometimes we get ourselves into trouble when we overinflate the TRL of the experiment that we've just conducted, and we take things out to the field before they're really ready. So to solve that problem, we're trying to get a little bit more granular on what do we really mean by the validation of a requirement? How can we look at a requirement and understand how mature it really is, right? So again, it comes down to formalizing what those requirements look like, formalizing the engineering connections that we have between those requirements and the tests that we've done, and then developing metrics maybe, right, that are that give you some information about how mature that requirement is. So we, sort of whiteboarded out like what would we want in an RML value, or requirement maturity level value. We want it to have a few properties. We want the maturity of a requirement to go, and maybe I should explain the bipartite graph first. As we build up these requirements and we mature them more and more and more, every time we mature them because we've just tested them, right? So you can think of there being this graph between the requirements that we're interested in and the tests that we've conducted. And a requirement could be tested in multiple times. Every time you do test it, you should have gotten smarter, right? So more testing means your RML goes up. But we wanted it to kind of track with the TRLs. So we didn't want to, if you test something with a TRL4 system, you shouldn't be able to say that your requirement is maturity level 5, for example. It's only as mature as the technology that you've tested it with. And if you've tested with low TRL deliverables, you've sort of learned less than if you tested with high TRL deliverables. And we spent a little while at the whiteboard and hammered out a formula, a metric that satisfies these, and started playing with it, and it's pretty interesting, and it's pretty telling. This is fairly recent work. We haven't explored it fully. We kind of changed the constant 2 there to get different performance and fine tune it. But the point is, like, this is only possible through, all the structure and the holistic architectural development that we've done, and it's about taking advantage of the structure that we put together. And even this is a simplified version of what we want to do. What we really want to do is not just look at the TRL of the test deliverable that was done, but break it into its subcomponents and look at the TRLs of those. So along with all of this, the requirements have a decomposition, the test deliverables have a decomposition, and all this stuff needs to track. So it kind of brings us back to the category theory applications. So that's it. Those were my sort of sample survey problems. Thank you for taking your time to listen. I hope that it was somewhat sensible. Like I said, we'll post the slides, and there's lots of links that you can follow if you want to get deeper on anything. You can always reach out to me on my email. And then I finish up with a few other links here. Really strongly encourage people to go check out internships at NASA. I have 2 internships this summer for applied category theory, so I can send information about that to anybody if they're interested. Organizationally, we have University Leadership Initiative, where universities can, it's a special pathway for universities to engage with NASA on aeronautics problems. And I would just kind of point you to, some of the work that NASA is doing in digital transformation overall. And as I said at the beginning, NASA is really successful when we partner. We're not the smartest people in the room, right? We bring the smartest people into the room. That's how we succeed. So this link is a wealth of information. There's so many different ways to partner with NASA, some funded, some unfunded. Again, if you're interested, please take a look, and don't hesitate to reach out if you have any questions or follow-ups. That's it.
Thank you for the talk. I was kind of a bit intrigued about the focus on category theory in NASA. How big is the focus?
The focus is just beginning. I think we're going to have a couple of successes under our belt soon that'll expand the interest. It's me, a few interns, some partners at Johns Hopkins Applied Physics Laboratory, and we're sort of experimenting with it right now. Again, if there's promise, we could probably find some funding. We could bring more people into it. Oh, and I should say, actually, I have stumbled across some other folks in totally different domains that have, if they have, at least worked with ontologies, and some actually category theory.
There's a lot of risk in doing something like this. First of all, you need people who are highly qualified. And yeah, it depends. I can see why it fits certain kind of problems, but it's also you may need to combine it with some other techniques like optimizations and a lot of other expertise. So it's not an easy effort actually.
Mm-hmm. No, and it's all under the hood. Like this is under the hood, right? Like it's a good observation. It's a very advanced skill set that you need to do this building, but it gives us the structure underneath. We do have a formal methods group at NASA that's pretty strong. They've worked typically in like first order logic, but I think we're starting to turn them on to this.
Okay, so then it makes for formal verification, it makes sense to work on these kind of things. It's kind of, these kind of methods are very different than a lot of other standard methods. So you always kind of worry if you have corruptions in data, maybe these are methods that are kind of very sensitive to it, or how do they do with, in empirical settings, or, kind of statistical questions.
Yeah. In fact, I think the reason why we came to it in the first place was for a version of that. We're trying to unify, there's like 700 research activities going on all at the same time, right? Pointing at the same problem, but they're all using a little bit different language, a little bit different models, right? But they're all fundamentally essentially similar. And this is a way, there's some ways in here that can unify or find the places where, if people did it a little bit differently, then it would all synchronize.
I'd be very curious to hear where you think co-algebras might be useful, if you know them.
Yeah, so this is, I told you I'm learning, right? Yeah. So the co-algebras, I believe, are associated with the collaborative design, if I'm not mistaken. There's a chapter in the 7 Sketches book.
Is it because it like splits, it creates 2 threads of the same design, and then 2 people collaborate, and then bridges them?
Right.
You mentioned the work with generative AI, which was over 2 years ago now. So more recently, what have you learned by exploring LLMs, and are you still as enthusiastic as you were then, or are there more cautions that you think about?
So we learned a lot, besides the technical, we learned a lot about like the policy. We spent a lot of time we ended up having to set up our own system. And there's been difficult to get people to kind of adopt it or trust it or believe it, because people are afraid of hallucinations, etc. This has sort of, like this particular, the generative AI, we've sort of stalled out a little bit, mostly because of funding and some redirection of focus, not because there wasn't technical promise to keep going. We still have it running, like we still experiment with it, but we're not making advancements. Trying to think of the lessons learned. There is a paper. One of those links is the paper that's associated with this. Yeah, it's just stuff that we wanted to do. Like, for example, I shared this with the FAA, and our 350 requirements, they're low TRL requirements. Like, they're kind of fishy. Like, you're not going to build anything off of them yet. We showed this to the FAA, and they saw a lot of promise in it, and we were talking about taking their requirements, which they have many of, and they're super mature. But we ran into problems with the data, being able to share it. Some of it's confidential, and then funding streams kind of moved around. So it is something I hope we can get back to.
So, talking about LLM. So LLM is a special case of the foundational model. So did you try to build a foundational model for the creation or for something else that you need?
We didn't. No, that's an interesting question. I think I may have seen some things like this where they build a foundational model for helicopter design, and that's all. That's what it does. It just like designs helicopters for you.
What about use of digital twins at NASA?
Digital twin is a very hot topic, which would bring me personally back to ontology, because two people say digital twin, they don't mean the same thing, right? Like, it's taken a long time to get closer and closer to the definition that we're all working from. Yeah, digital twin is of significant interest. And we're tackling it in a lot of different domains. So, for example, the digital transformation link, you can follow that. You might find some things about where we're putting together digital twins of the buildings so that we can, control them better. The idea behind, I don't know which one to point to, but the idea behind this whole architecture system that we're, trying to put together is, in a sense, kind of a digital twin. Because the vision is that if you connect enough of the right data to it, it becomes representative of the experiment space, right? And then it's like digital twin of experimentation. We've tried to interconnect simulations. That never works. It is an important topic, and the FAA is pretty keen on it as well. Why? So I'm curious why you would ask.
So I just have some interest in it, and I'm curious what kind of problems you're facing. And so you also mentioned simulation, so you probably have issues with gaps between good real to sim gap, right?
Mm-hmm.
Yeah, I'm just curious the type of problems that you have.
Yeah. There's an example of digital twin, what I would call digital twin in the NAS today, where they, sort of take current conditions of the environment and predict traffic scenarios so that they can make decisions about what they do now. Is actually the demand capacity balancing capability. There's like a digital twin version of that.
So for traffic.
For traffic, yeah.
So what kind of models do you use for the dynamics of traffic?
It's typically just, like kinematic or kinetic, depending on your usage. 3 degree of freedom, sometimes 6, but not usually. But like physics simulations, we don't have anything more creative than that.
And you're talking about traffic, at the air, right? So you need to also know a little bit about nervous strokes and things like this. So in terms of, kind of motions of air and winds.
Yeah, that. Oh, well, yeah, a bit. So that brings in the weather problem, right? That's a whole problem all of its own. There are models of traffic, like, Eulerian models and Lagrangian models of traffic that there's good research on, but I've never seen it implemented anywhere. When we model traffic, it's just brute force, just simulating a trajectory from A to B for the most part. Yeah. But those are the types of things that, could be powerful. You get creative.
You mentioned a little bit like policy stuff with ChatGPT. I guess I'm curious about like how much of your work is trying to solve like technical challenges, like I need to solve a problem in category theory versus like a policy issue or like an adoption issue, like you said, people didn't want to like
Right.
necessarily like trust the algorithm experiment.
Yeah. It's a lot of non-technical work in industry, and it kind of depends on like where you want to go, right? Like, if I had more discipline, I might be able to keep myself just to technical problems. But it's always the non-technical problems that are like the biggest challenges, right? Those are like the hardest engineering problems to overcome. And it kind of depends on what you mean by that too. Like one of the taglines I use sometimes is like, it's people, processes, and tools, right? Like those three things working together is how we do anything. We always focus on the tools. That's the technical, right? I can build this thing. I can do fancy stuff. That's easy. It's the people using it that's hard. And it's the processes that manage everybody together. That's hard. And your question has multiple layers because there's really important, significant work associated with getting regulations right. That's where this study was coming from, trying to analyze like what's the closest safe separation that you can still maintain safety. It always ends up, it's not done until all the people have argued about whether 10 to the minus 9 or 10 to the minus 8 is the right safe number, right? So like that's just part of your engineering. It's part of the problem when you get in the industry.
Question. I'm not sure you can answer this question actually, but I was just wondering, as we were talking about NASA and its space initiatives and what's been happening lately on the commercial side as well. And specifically from a systems engineering point of view, do you have any sense of whether or how things are being done differently by, SpaceX or Blue Origin or any of these others compared to how NASA does it? I mean, certainly the speed with which some of these developments have happened has been quite impressive.
Yeah. This is a great long conversation to have. First, I would say NASA's mission is like to advance humanity, like literally, those are the words. And we accomplished the mission by doing the crazy stuff that's far out there, right? And once it gets to a certain maturity level, like we don't work past TRL6, we get rid of it, right? We want industry to take it over. So SpaceX and the space industry blossoming was really kind of by design. This is what we wanted, and that's why we can move on. But what are they doing differently than what we're doing? A lot, or what we've done, what we've been doing. We can tend to have a lower level of tolerance for risk. Like the failure is not an option mantra. Safety is number one, as it kind of should be. But there's like a balance in there that maybe the federal government is not the one to strike the best balance on. On the other hand, I think what you see, what we've seen certainly in like some of the artificial, the driverless cars and domain in particular, it's kind of swung the pendulum the other way. where, yeah, we're getting great data and we're getting great performance, but it's at the expense of safety. But if you're willing to take that hit, then you can move quick. That's kind of one of the things that they did. The other thing that's different, like SpaceX is a great example. The Artemis rocket that we're working on now, which is like, I don't know, $1 billion over budget or something, is very expensive. The SpaceX rockets, they're like 100 million each, right? They could break and it's fine. They're just going to do another one, right? It's like, you know, they could burn 10 of their rockets and it won't cost as much as one of ours. That's agile, right? I mean, like that's agility, which has come into our engineering culture, which is super important and super right to get done, because that's how you solve this problem. You have to be agile, right? You have to find your problems. This is what fail quick means. It means fail here, don't fail here. The government often, the bureaucracy of the government has constraints that businesses don't. Budget cycles, politics. We can't just blow up rockets because constituents are going to get upset, right? So that's one of the dynamics in there as well. I think we both have a lot to learn from each other, industry and government. And one of the things that our mission director always reminds us of, or you know, sort of as one of his goals, is to build a little bit of a new public-private partnership. The way that government works with industry and the way that industry works with government and academia and everybody needs to change a little bit, right? Government needs to be a little bit more agile. Big companies and small companies need to be able to come together and work well and efficiently. You need government in there to like keep the playing field level, but not too much so that we constrain innovation. It's a tough balance.
Thank you very much.